Welcome to this spoken tutorial on metal displacement reactions using Vlabs. In this tutorial, we will learn to carry out displacement reactions of magnesium, zinc, lead, copper and silver. Arrange metals in decreasing order of reactivity. To follow this tutorial, you should be familiar with ChemCollective Vlabs interface. If not, for relevant tutorials, please visit our website. Here I am using Mac OS version 10.10.5, ChemCollective Vlabs version 2.1.0, Java version 8. Here I have opened Virtual Chemistry Labs application window. Default lab setup window opens. Click on File menu and select Load Homework option. Default lab setup dialog box opens. Double-click on Redox folder. Then double-click on Redox reaction series. Click on Problem description in the Stockroom Explorer. The problem states that perform metal displacement reactions. Arrange the given metals from strongest to weakest reducing agent. Stockroom Explorer is provided with all the required metals and their salt solutions. Let us define redox reactions. An oxidation-reduction reaction involves transfer of electrons between two species. Oxidation is loss of electrons by any species. Reduction is gain of electrons by any species. Metal displacement reactions are a type of redox reactions. In metal displacement reactions, a more reactive metal displaces a less reactive metal in a metal salt solution. This slide shows the activity series of some metals used in displacement reactions. Here is an example of metal displacement reaction. Silver ions in silver nitrate can be replaced by copper to form copper nitrate. Elemental silver is precipitated in the reaction. Silver has lower oxidation potential than copper. It cannot replace copper from copper nitrate. Switch to Application window. Click on Workbench 1. Right-click on Workbench tab to rename. Type name as Magnesium Reaction. Let us now demonstrate the reactivity of magnesium metal. From the Stockroom Explorer, click on Solids cabinet. Double-click on Magnesium. Click on Solutions cabinet. Double-click on 0.1 m copper nitrate, 0.1 m zinc nitrate, 0.1 m lead nitrate, 0.2 m silver nitrate. Close the cabinets. Click on Glassware menu and select 250 ml Erlenmeyer flask. We need 4 flasks for this experiment. Make duplicates of the Erlenmeyer flask. Rename the flasks with corresponding metal symbols: zinc, lead, silver and copper. Arrange the apparatus and chemicals. Click on any one of the bottles containing solution. The solution info panel shows the bottle contains 50 ml of solution. Pour the contents of the bottles into respective flasks using precise transfer mode. Type 50 in the transfer amount input bar. Click on Pour. Similarly, transfer contents of the bottles into flasks. Keep the empty bottles aside. Click on each Erlenmeyer flask and note the concentration of the metal ions. Pour 1 gram of solid magnesium metal in each flask using precise transfer mode. Click on the flask containing copper nitrate. Observe that green color of the solution has disappeared. Temperature increases on addition, then decreases. The reaction is exothermic. In the solution info panel, concentration of copper ions is 0. Magnesium ions are observed in the solution. This means that magnesium has displaced copper ions from the solution. Click on Solid Radio button. Observe that metallic copper is now deposited in the solution. This is because magnesium has higher oxidation potential than copper. Click on the flask containing zinc nitrate. Click on Aqueous Radio button on the Solution Info panel. Concentration of zinc ions is 0. Magnesium ions are now observed. Click on Solid Radio button. Observe that zinc is now found in the solution. Magnesium has replaced zinc ions from its solution. Click on the flask containing lead nitrate. Observe the Solution Info panel. Magnesium has replaced lead ions from its solution. Click on the flask containing silver nitrate. Observe Solution Info panel. Magnesium has replaced silver ions from its solution. Now let us demonstrate the activity of zinc. Click on File menu and select New Workbench. Rename the workbench as Zinc Reaction. From Solids cabinet, select Zinc. Click on Solutions cabinet and select 0.1 m copper nitrate, 0.1 m magnesium nitrate, 0.1 m lead nitrate, 0.2 m silver nitrate. Close the cabinets. As we did in the previous experiment, take 4 Erlenmeyer flasks. Rename the flasks with corresponding metal symbols: magnesium, lead, copper, and silver. Arrange the apparatus. Pour the contents of the bottles into the respective flasks. Type 50 in the transfer amount input bar. Click on Pour. Pour 1 gram of solid zinc metal in each flask. Type 1 in the transfer amount input bar. Click on Pour. Click on the flask containing copper nitrate. Observe that copper is displaced by zinc. Click on the flask containing magnesium nitrate. Zinc cannot replace magnesium from the solution because zinc has lower oxidation potential than magnesium. Hence, there is no reaction and zinc remains in the solution. Similarly, click on flasks containing lead nitrate and silver nitrate. Observe that zinc displaces both lead and silver. Similarly, perform the experiments for lead, copper, and silver. Open a different workbench for each metal displacement reaction. Rename the workbenches as lead reaction, copper reaction, and silver reaction. Required metals and salt solutions are available in the Stockroom Explorer. We have performed these experiments. Here are the observations. We have tabulated the results as shown. Magnesium has higher oxidation potential value. Magnesium displaces metal ions zinc, lead, copper and silver, which have lower oxidation potentials. Silver with lowest oxidation potential cannot displace magnesium, zinc, lead or copper ions from solution. The order of reactivity from strongest to weakest reducing agents is as follows. Let us summarize. In this tutorial, we have determined the order of reactivity for the following metals: magnesium, zinc, lead, copper and silver. As an assignment, perform displacement reactions using solutions of metal halides. Establish the order of reactivity of halogens. The required chemicals are available in the Stockroom Explorer. The video at the following link summarizes the spoken tutorial project. Please download and watch it. The Spoken Tutorial project team conducts workshops using spoken tutorials and gives certificates on passing online tests. For more details, please write to us. Please post your timed queries in this forum. Spoken Tutorial project is funded by NMEICT MHRD Government of India. More information on this mission is available at this link. This tutorial is contributed by Snehalata Kaliappan and Madhuri Ganpati from IIT Bombay. Thank you for joining.